simplest quantum algorithm there is. Yeah, you would never guess by this, let alone, I don't even know how to type half of that. So from a practical, commercial programmers writing software, say, or even someone not that well versed in programming or quantum computing, this represents serious challenges. So what I've done is I've come up with a new solution that I've called Cove, and essentially this is a framework for programming quantum computers. It's a framework that I built on C#, so I get all the power for classical computation built in, C#, and .NET, which forced me to only tackle the quantum computation part. Another key point is, but as a framework, it's meant to be extended. People can derive, new operations. They can add on functionality to registers and so on beyond what I've provided. The third kind of key point is programming against interfaces and not implementations. What I've done is I've separated things, created a set of base interfaces, basically, that would say, hey, if you want a qubit, here are the operations you have to provide. And then there's a second set of implementation, which is actually the how you carry it out. So it's kind of separated into the what you have to do and then how you have to do it. The kind of idea behind that is that I can write my code against the interfaces, and then as long as the implementations kind of conform to that and the behavior, I can switch them out. So I can write code against a simulated quantum computer, and then later on, when, hopefully, we have actual quantum computers, I could then just replace the implementation of my code ideally would run just the same. The current work that I have includes that simulated quantum computer. It's really a prototype still, but it allows you to kind of execute the code and see what happens. But the key problem with any simulation of a quantum computer is you get an exponential slowdown. So I started running into memory problems around a dozen qubits or so. So really trying to do like that previous example where we talked about needing 384 qubits, just can't be done. So why is it a new contribution? Provides extensibility, not present in the tellies. Really gives us kind of the object-oriented approach for quantum computing. Another key point is that the documentation is important as a framework itself. For any framework to be usable, the documentation, it has to be there. Otherwise, you have a significant learning curve, and it just makes it difficult to use and increases the cost of using whatever that approach is. And that documentation is available on my website, which I'll post a link for at the end. Within the code itself, if you're using Visual Studio, it will show up in IntelliSense also, and then finally an independent help file. And really what I've tried to do too, in addition to all this, is I've really tried to avoid these, what I've kind of deemed usability flaws in the existing proposals. I thought, looking at all these proposals, oh, this makes it hard to use, that makes it hard to use, and I've kind of identified, those flaws and tried to avoid repeating them and provide good solutions. So here's a simple example of what's called quantum entanglement. That basically means the measurement of one qubit impacts the state of another. This doesn't happen on a classical computer. If I flip one bit off and on, that doesn't impact any others whatsoever. With entanglement, I could entangle two qubits, keep one here with me, send the other to the other side of the galaxy, and then when I measure my qubit, say to 0, the other qubit will also be 0 at the same time. That kind of toggling or measuring a single qubit impacting others isn't possible classically. This code snippet is pretty simple. First line, just to declare a quantum register of 2 qubits. You can see here I'm declaring against the implementation, assigning it to the interface here. And then I create a result to hold the answer. And then basically entanglement requires 2 quantum operations to entangle the 2 qubits. So I carry those out here. This part here, the slice 2, is just saying essentially give me only the first qubit and then perform the Hadamard operation on it, and then I perform what's called a controlled knot on the entire register. And a controlled knot is essentially if the control qubit's 1, flip the target qubit. If it's 0, you don't do anything. And then we just measure it, assign it a result, and then display the result on the console. Here's a second example of doing a sum operation. I won't go into this in as much detail. Really, the only key point with this is that the result is essentially a list of quantum operations. As I started writing the code to perform the factoring example, it came up, okay, how do you do a sum operation? How do you do a carry, et cetera, et cetera, et cetera, in a way where you know, it doesn't really matter which qubits you're targeting. You know, I may want to sum qubit, you know, 5 and 12 on a register. You know, so how do you do that? And the solution for that I came up with is you specify your target indexes, and then you'll just get back to series of operations that perform that. And using this approach too, you can build up from the simple cases such as sum to you know, modular adders and so on, just by you know, kind of chaining these all together. So reflections, I did a lot of unit testing to kind of show myself that I was you know, carrying this out correctly, that my simulation was correct, and so forth. And that really led to a much more solid design, because I had to write myself a lot of code using Cove. This isn't just some design I came up with and threw out there. I really had to write you know, thousands of lines of code to test it. And in that process, I would be like, oh, this is kind of a pain the way I have it now. You know, if I added this in, it would be a lot easier, and I would do that. So it kind of led to an iterative cycle. You know, I'd kind of build it up more and more. As I wrote the test, I would refine it further and further. The second one, well, in hindsight, it should have been expected, but the implementation of the simulation was much harder than I anticipated. Things I thought would take me maybe days would end up taking weeks. A large part of that is that many of the problems with implementations aren't documented well. Two big ones I ran into was what I would call reordering of operations. You have the operations defined by your 2n by 2n matrix. And you'll get it in standard form. You know, here's your C0, you know, with the target qubit being 1 and the control 0. What if you want to flip them around? What's the matrix look like then? That was not documented well at all. In all the papers and books I read through, which was pretty much everything I could get my hands on, I only found that in 2 places really. And expanding the operations to match the register size, I only came across that in 1 place. And what I mean by that is the standard like C0 operation, for example, operates on 2 qubits, but the matrix has to match the size of the register you're applying it to, just through you know, regular linear algebra. So how do you expand that operation where you can then apply it? So really it was lack of literature, essentially. And then the memory and time constraints limited what I could do, as I said earlier on. That really made debugging difficult. You know, when you have you know, a million complex numbers, any one of them are off, your simulation is not going to run right. And only being able to do a handful of qubits, you know, really kind of limits things. You can't scale up, which is kind of what I wanted to do a little bit more of an